All right, so that gives you the general addition rule, which is basically a formulaic approach of saying what I was saying on the previous page. In terms of the way the AP likes to write it, A union B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. All right. For mutually exclusive events, there's no overlap, so there's nothing to subtract. So it's irrelevant. I don't know why I have so much space there. It's not really necessary. So, not needed. So that's a typo for somebody. Same deal here. All right, so I'm going to pop a star onto this example set because you'll try those on your own. And then I'm going to hop on over to multiplication. Bless you. For the first one, would you say getting a king or a 7 or a king is mutually exclusive? Can you get a 7 or a king at the same time? No. So we're just looking for the probability of 7 plus the probability of getting a king. All right, so this is mutually exclusive. Two events that can't occur at the same time. All right, so 4 out of 52 plus 4 out of 52 is going to be 8 out of 52. All right, now what about 7 or prime? Can you have a set of values that are 7 and prime at the same time?
Yeah.
Yeah, so this is not, so a little tilde symbol there, not mutually exclusive. So what I'd have to do is find the probability of getting a 7 plus the probability of getting a prime minus the probability of getting a 7 and a prime at the same time. Now, you can take a more intuitive approach to this, where on the fly you're not double counting, but I'm going to just take it through the formulaic approach, because there are 4 cards in the entire deck that are 7s. Now, out of the sample space related to the deck of cards, so the numerical values span from 2 to 10, all right? But then that's pretty much it. The face cards and the aces don't have numerical values. So the primes would be 2, 3, 5, and 7. So for each suit, so there's a total of 16 of them. But we would have been double counting the 4 7s. So as it turns out, because the primes actually encompass the set of 7s, we're looking at 16 out of 52, which happens to be the probability of getting a prime number in a deck of cards as being the only probability that's relevant. All right. Prime or even? Mutually exclusive or not? Not, so not mutually exclusive. All right, so same idea, probability of prime, which we know is 16 out of 52, because we just figured that out. Oh, 25, look at that. That is a first day of the week mistake. Plus the probability of getting an even number. All right, so we got to think about the evens. 2, 4, 6, 8, 10, right? So that's a total of 20 values in the deck. And so I just need the probability of a card being prime and even at the same time. All right, so that upside down U, or at least my attempt at drawing an upside down U, is a symbol for and, right, or the intersection between two sets. So how many cards in the deck are both prime and even at the same time? 4 of them. So we're looking at 32 out of 52. All right. Now, probability of 7 or red is the same as, oh, sorry, 7 or not red is the same as the probability of 7 or black. So is that mutually exclusive or not? Not. All right, so probability of 7 plus probability of black minus the probability of the intersection between 7 and black. So 4 out of 52. How many blacks in the deck?
26.
26, half the deck. How many are 7 and black at the same time? 2. All right, properties. It's pretty straightforward also. Multiplication rule deals with multiple events. So 2 or more trials are being conducted. Now we're starting off with cards, but we're going to get into contextual situations, so it's going to get a lot more complicated. So, but if we can get the groundwork when dealing with cards, dice, and things like that, then things will be a lot easier. A coin is tossed and then a die is rolled. Construct a tree diagram for a flip of a coin. All right, so heads, tails. And a roll of a die, and find the probability that you would toss a heads and roll a 5. All right, it's implied that you'd find that from the tree diagram. All right, so if I flip the coin, I could get a heads, but then after I roll the die, I could get any of the outcomes from 1 to 6 on the die. So 1, 2, 3, 4, 5, 6. Same thing for tails. All right. So the first trial, you got to kind of think of the first branch as being the experimenter. You know, I'm flipping the coin, so this is me, the beginning of the tree. I would want to include probabilities for each one of these outcomes. So the probability getting heads would be 1 out of 2. Same thing for tails. All right, the probability of rolling a die, well, it's an independent event, so it doesn't really matter whether I got a heads or tails. The probability of getting a die to come up as a 1 is going to be 1 out of 6. Same thing for 2, 3, 4, 5, and 6. So each one of these has a probability of 1 out of 6. So it kind of stinks because you have to write all these probabilities in anytime you make a tree diagram. Which means that if it were 3 flips of a coin and 3 rolls of a die, well, it would take the better part of the day, I think. So each one of these would have a corresponding probability associated with it. So multiple events means multiplication, because I want the 1/2 to occur first and then the 1 and 6. So I'd be looking at a product of 1 out of 12. And that would be, because this is a uniform distribution, 1/12 all the way through. Now, because it's uniform, you didn't really have to label all these values in order to figure out that it would be 1/12. because if every event is equally likely to occur, then since you have 12 equally likely outcomes, you'd be looking at each one of them occurring 1/12 of the time. All right, so you could get it that way, but only because it's a uniform distribution. If it were not uniform, so let's say it were a dependent situation where you're dealing with maybe two cards being selected from a deck and you had to make a tree diagram, then if you didn't replace the first card before you selected the second one, then the probability of selecting the second one would be impacted by the fact that the first one was selected. All right, so not the case here, but it could be. And so you'll see that when you get to the examples that follow. But I mean, in this simple case, it's like if you just needed for independent events to find a probability, you just multiply them together, 1 out of 2 times 1 out of 6, and you get 1 out of 12. It's when you have dependent events, that's a different story. All right. So I'm going to pop a star on these problems. So you could try those on your own also. Those are a little bit more interesting than the ones on the previous page, but definitely very doable. And then the last thing, so on the next page we talk about the multiplication rule. Multiplication rule is pretty straightforward when you're dealing with independent events, but when you have dependent events, you got to do a little bit of thinking, and that makes things complicated. So the order is implied whenever you're asked to find the probability. When it says find the probability of a king and an ace, it's implied that they're talking about in that order. So there's an implied and then. So king and then an ace, even if it didn't say in that order. All right. So it's only when they say in either order that you have to assume that they're asking for one way or the other. All right. So in the case of number one, it's not bad because even though it's a king and an ace, and one card is being withdrawn, not replaced before the second card is selected, it's not going to be hard to figure out what the probabilities are. All right, so what I'm going to do is I'm going to denote this as the probability of getting a king times the probability of getting an ace vertical slash k. All right, and what that tells me, this little guy right here, is saying the probability of getting an ace given the first card selected was a king. All right, getting an ace given that the first card was a king. All right, it's the conditional probability. When you're dealing with dependent events, there has to be a condition applied, and if that condition is not met, then you really can't go any further. But you have, in most cases, there is a condition. You just have to kind of determine what that condition is causing in terms of an effect. All right. So, what is the probability under ordinary circumstances of getting a king? 4 in 52. Now, always assume success with probability. These are multiple events. So I selected a card. Turned out it was a king. Doesn't matter what kind of king. You selected one of the kings from the deck. So pick your favorite king. Hearts, diamonds, clubs, or spades. It doesn't matter. How many aces are left in the deck? 4. How many cards overall are left? 51. All right. So this part here is telling me the probability of getting an ace given that the first card selected was a king. All right, so we're looking at 16 over 2652. Now, the second question says probability of king and an ace in either order. All right, so this, well, either is implying an or. All right, so this is saying a couple of things, and we'll make use of our answer to part one. It's saying the probability of getting a king then an ace, so king and ace, or
Ace, then king.
ace and then a king. All right, king and an ace in that particular order we already figured out was 16 over 2652. So we're not going to reinvent that wheel. If you're looking for the probability of either of two events occurring, it's some addition rule. So I'm going to add these two individual probabilities together. But what I do need to find is the probability of getting an ace multiplied by the probability of getting a king given that an ace was drawn. Now, there often will be symmetry. So, and not always guaranteed, but in the cases of cards, dice, things like that, you could expect that to be the case. But not always. So, don't fall in love with the shortcut to this, which is just basically going to be to double the probability of going in one direction. So probability of getting ace is 4 out of 52. An ace was successfully obtained, which means I still have 4 kings left in the deck, but there's only 51 cards, so I still have 16 over 2652. But I'm adding that to the previous 16 over 2652. All right. Now, it's pretty important to realize that or represents kind of a reset button on the whole process, because these two events aren't happening simultaneously. It's one or the other. So you're either getting a king and the ace when you draw 2 cards from a deck, or put all the cards back in the deck, shuffle them up, you're getting an ace and then a king when you select 2 cards from the deck. Both are not happening simultaneously. It's one situation or the other. All right? So you have to think of it as a reset button where all the cards are being put back in the deck every time you have a plus sign or an or in one of these probability questions. All right? So 32 over 2652.
Is it okay if we simplify this when we give our answers, or?
It's okay, yeah. It's totally fine. Not required, though. All right? In a lot of cases, you'll just write down a simplified answer because that's what the calculator is going to give you. So if that's the case, then by all means. But just know that it's never going to be a requirement for probability for you to simplify fractions. The bottom line is the unsimplified form of each of your probabilities will always give you, if you're dealing with a common themed kind of relationship, they're always going to give you a common denominator, which is great if they're in unsimplified form. So then it's just a matter of adding, subtracting numerators. So if you simplify, sometimes it makes your life a little bit trickier. The one thing I actively discourage you from doing, where possible, sometimes you can't avoid it, would be to go to decimal form. Decimals, they introduce an unacceptable amount of variation into your solution, and it's just disgusting. All right. So number 3, 2 cards of the same suit. All right, so that's telling me that I'm looking at, well, for a deck of cards, we're dealing with a pair of diamonds, diamond and diamond, or heart and heart, or spade and spade, or club and club. Definitely can't draw. But again, each or represents a reset button. So How many diamonds are there in a deck of cards? 13 out of 52. You selected a card, turned out it was a diamond. How many diamonds are left? 12. How many cards are left? 51. All right, so for this calculation, we get a product of 156 over 2652. The reset button, the OR, has us putting all the cards back in the deck and starting over. All right. If I do that, well, I still got 13 hearts out of 52 cards. If I select one, I'm still only going to have 12 out of 51. So 13 out of 52 and then 12 out of 51. I'm going to get the same value. So then it begs the question, is there any reason to think that the values would be any different for spades than for clubs? No. So why not just take 4 and multiply it by 156 over 2652? All right, if you do that, the result is what, 324? 624, duh. 324 would be some conglomeration of multiplying by 2 and 4 at the same time. 2652. All right, so 624 over 2652. Now, for your own purposes, maybe you go to decimal form so you get a sense of the percentages. All right, so 624 over 2652, maybe you don't feel what that number is all about. Right? It's around a quarter, maybe a little bit more, maybe a little bit less. But it's in the neighborhood of 1/4, so 25% of the time you could expect to have 2 cards dealt with the same suit, roughly. But to answer the question, 624 over 2652 is perfect. All right. Now, you want to apply this to playing poker or something like that, then you could see the applications. But the thing is, with poker, you got a lot of other variables coming into play. It's not just 2 cards dealt at random to people, and that's the game. You know, there's more to it than that. All right. 2 cards of the same value. So that would be 2 and 2, or 3 and 3, or 4 and 4, or, and so on, all the way up to ace and ace. All right. The jacks, queens, kings, and aces, they don't have any numerical value, but all jacks are equal to one another, all queens are equal to one another, kings are equal to one another, and aces are equal to one another. All right, so they have the same value. They're just valued at A, for example, or J. All right. So if I select a 2 at random from the deck, what's its probability? 4 out of 52. Probability of getting another one?
3 out of 51.
3 out of 51. So 12 out of 2652.
Does that number just become all too familiar?
It does, yes. That and 2704, which is 52 squared.
Just looking at this though, now wouldn't, since the odd of drawing a card of value X is 1 in 13, but since we then have to have 13 different arrangements of that, isn't this just the exact same thing as determining the probability of finding one value given, or I'm not wording that well.
Well, we're not, it doesn't seem like we're accounting for the different arrangements of each of the values, but we actually are, because that 4 and 3 multiplied gives us the number of arrangements of 4 things taken 2 at a time, the permutation, which we'll get to. But so that allows for the different ways in which the 2s can be organized. So that's giving us all the different probabilities of getting a pair of 2s, allowing for the 2 of hearts to go with the 2 of diamonds, the 2 of clubs to go with the 2 of spades, the 2 of hearts to go with the 2 of spades, and so on. So it's accounting for all of the arrangements, possibilities. Lost the word.
I guess I just mean that since the first fraction is effectively it's 1 over the amount of different values we have, then isn't the answer simply going to be the number is multiplied by in the end? Because we have that amount of values that will be added up.
As it turns out, yes.
Yeah.
Because we're going to take the 1/13 and multiply by 13, yeah. So the sum of all the second values, yeah. Good observation. So we're going to take, sorry, we're going to take the 12 over 2652 and multiply it by the number of possible pairings. If I can get my pen to work. Which would be 13. And again, the unsimplified form is fine, 156 over 2652. But as you were saying, that would be the same as 12 out of
3 over
3 over 51. Right, yes. Out of the way here is really just me slapping a star just on this whole section here, because I'd rather you try that first on your own before I go over it all with you, because the formula is there. It's just a matter of you seeing if you can figure out a way to apply it. All right. So then the concept of conditional probabilities complements the conditional probabilities, the idea that I asked you to explore a little bit on your own. It's pretty straightforward. It's by rule, but I'll talk to you about how the rule works and why it does. And this is going to tie together with normal probability. So it's kind of an interesting thing to think about. So this is telling us that the probability of at least 1 is equal to 1 minus the probability of none. And we know that at least 1 means 1 or more. So let me just create a quick probability distribution. Something fairly simple. So let's say you have x and p of x, the x values and the probabilities that go along with them. And let's say probability of getting no success whatsoever was 0.5. All right, so the probability you're going to fail is substantial. All right, probability of getting 1 success is 0.2, and probability of getting 2 successes is 0.3. All right, so that gives us a total of 1, so we know that we're in good shape. So the probability of none would be the same as the probability of getting 0 successes, which in this case would be 1. I'm sorry, 0.5. The probability of at least 1 could be thought of as the probability of getting a success of 1, or 1 success, plus the probability of getting 2 successes. Now you can see the drawback to this approach would be that if I had 3 successes, x is 4 successes, 5, 10, 20, 100 successes, at least 1 could be a nightmare. All right? Nice. So you could be looking at a kind of distribution that would require you to add up a lot of values. Now, if the table's already given to you, it's not a big deal. But what if you had to figure out those probabilities all on your own? All right, that could be a problem. Here, it's not a big deal. 0.2 plus 0.3 is equal to 0.5. But the other way to go about it would be to say the probability of at least one is equal to 1 minus the probability of none. So 1 minus the probability of 0 successes, which would be 1 minus 0.5, which is in turn 0.5 also. All right, so basically at least one, which is this part, could be thought of as everything except for the part that you don't want, which is the none. Let me make that red. All right, so if you think about it, when push comes to shove, if you have a choice between determining one probability or determining multiple probabilities, 2 probabilities may not be bad, but it could be a case where you have to determine 10 probabilities in order to find probability of at least one. Right? The idea that all you'd have to do is find the probability of none, no successes whatsoever, and subtract it from 1, that's not bad. All right, so we apply it to coins first, then dice, and then we get into some real world applications down the line. Right? Probability of tossing at least one head would be the same as probability of, so at least one head would be 1 minus the probability of no heads in 2 tosses of a fair coin. All right. If you're not getting any heads, that means that in both tosses you got tails. So probability of getting tails and tails. Now those are 2 independent events. All right, which means that the probabilities will be unimpacted by success or failure in previous trials. So what's the probability of getting tails when you flip a coin? 1/2. All right, flip a coin a second time. What's the probability of getting tails? 1/2 again. So we're talking about 1 minus a quarter. So the probability of getting at least one heads in 2 tosses of a fair coin is going to be 3 out of 4. I can verify that by listing the sample space. Heads, 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 tails, tails, heads, tails, tails. The cases where I have at least one heads, first 3 cases. One where I don't is tails and tails. So 3 out of 4 instances in which I have success. All right. Same structure for the next one. Probability of at least one heads. This time 3 tosses. So 1 minus what?
1/2 cubed.
1/2 cubed. So 1 minus 1/8 is going to give me 7/8. All right. Maybe you're fine listing the sample space for 2 tosses of a fair coin, even 3 tosses of a fair coin. Probably not going to be overly thrilled about doing it for 37 tosses of a fair coin. So probability of at least one head. This is where I kind of prove my point. 1 minus 1/2 to the what power? 37th power.
Did you compute it?
Will in a moment.
Did you do it?
just showed up as 1.
It just shows up as 1. 0.5.
So 1 minus
Yeah, 1.
1/2 to the 37th. So it's saying that, right?
Yeah.
So it's saying damn near 1, but okay, so we don't want to write that. So let's tackle this a little differently. Let's do 37. Oh, I'm sorry, 2 to the 37th power. All right, so that's our denominator.
It's 1 less than that.
It's 1 less than that. Because there's only one instance where you would have none. So you're looking at 137, 438, 953, 471. Some good stuff, right? All over the same number ending in a 2. How you doing?
If you have a box plot and you hit trace and find the you don't see the value or something, you know how to fix that?
It doesn't show up?
It doesn't show up. And I'm looking online and I can't seem to. I went to format.
That's new.
Yeah.
And-
Okay.
Try hitting zoom 9 first.
I did. So not helpful, Mr.
Crikey.
It's the early.
137. Yeah, that's weird. I've never seen that before. 438 953 472. All right, so basically just finding a common denominator. So not too bad. The die is rolled 6 times. So probability at least 1 6. At least 1 4, sorry. So 1 minus probability of getting a 4 would be 1/6, but I want that to happen 6 times. And we want it to happen, sorry, 5 6. We want everything but that number.
Well,
All right. So the probability of not getting a 4 would be 5 out of 6. I want that to happen 6 times.
Oh, no, you're right.
So 5 6 to the 6th. Subtract it from 1 and you have it. So this one's a little weirder, but the way we would handle this is 5 to the 6th is that. 6 to the 6th is that. So we're looking at 1 minus 15,625 over 46656. And then with our common denominator, we're just saying 46656 minus the 15,625. So we're looking at 31,031 over 46656. All right, so you get a nice exact value. In this case, I think we would agree, nice exact value. Whereas in number 3, I would not call this a nice exact value. I'd call it an exact value. I wouldn't qualify it as being nice. All right, so we're gonna do a lot with these rules because we're gonna expand these rules into the world of conditional probability, and then also we're gonna tackle some other things related to continuous data sets. So it'll be pretty interesting stuff coming.